Hello and welcome to the webinar. Happy Friday. The topic today is how to accelerate genomic sequencing with NVIDIA, Clara, Parabricks, and FlashBlade S. This event is brought to you in partnership thanks to our friends at Pure Storage and NVIDIA. We've got a great event lined up for you today. This is going to be a really cool discussion. And I mean, this is a really cutting edge hot topic. Before we get started, there's just a few things that you should know about the event today. First off, my name is David Davis of Actual Tech Media, and I'll be serving as the host. We always want these events to be educational, and we encourage your questions there in the questions pane of the audience console. We welcome your hellos and greetings, but we also want your technical questions on the topic of the day. So keep that in mind as you're listening to the presentation and discussion. At the end of the webinar, I'll be announcing the winner of the Amazon $250 gift card drawing. If you're watching this recorded or on demand, of course, that drawing would have already occurred. The prize terms and conditions can be found right there in the handouts tab. And speaking of handouts, don't forget about the first link there in the handouts tab. It is a link to gain additional information on the topic here of the event, accelerating whole genome sequencing with NVIDIA and Pure Storage. It's a really nicely done resource, so make sure that you check that one out. All right, with the housekeeping information out of the way, it's now time to bring in today's expert presenters. Welcome to Bikash. He is a technical director for DevOps and software build solutions at Pure Storage, and Jason, who is an industry business development representative at NVIDIA. Bikash and Jason, it is great to have you both on from Pure Storage and NVIDIA. Take it away.
Great to be here today, and pleasure to share some information on genomic sequencing analysis with the great audience here. Just to give a little bit of a preview for what we're going to go over today, I'm going to give an introduction to NVIDIA and NVIDIA Genomics, then dive into Parabricks, which is our solution for accelerated genomic analysis on GPUs, then hand it over to Bikash, who will talk about modern data challenges in genomics, as well as go over some specific results using FlashBlade alongside NVIDIA Parabricks. All right. So for those of you who are not too familiar with NVIDIA or maybe know NVIDIA as a GPU company, we've expanded well beyond that. To today, we have CPU solutions and DPU solutions on the hardware side, so 3-chip architectures. And then we build those chips into systems, servers like the DGX system or OEM servers. And that's really on the hardware side. But on top of that, we are a full stack software company too. We have acceleration libraries for various workloads. All the way up to the top, we have domain-specific applications, AI frameworks, and tools to accelerate workloads in specific industries and applications. Just like Parabricks, within our healthcare and life sciences industry, Parabricks accelerates genomics. So lots of work NVIDIA is doing today. Today, we're going to focus on genomics. So why NVIDIA and genomics? Maybe the primary reason is the explosion of data. So since the first human genome was sequenced years and years ago and cost millions and millions of dollars, the cost of sequencing has gone down tremendously over time to where we have the newest sequencers can sequence a whole human genome for as little as $100, which is really amazing for democratizing genomics, making it easier to sequence every individual, get diagnoses quicker and faster than ever before. At the same time, though, that reduction in cost also results in a huge explosion of data. There's more sequencing being done. By 2026, in the next decade, we expect to exceed 40 exabytes of genomics data. And this quote on the right by the NHGRI, which is part of the NIH, emphasizes the importance of genomic data science and computation to enhance our ability to sequence DNA and extract insights from genomic data. So more application specific, why is it important to accelerate genomics beyond just getting through all of that data? The first one, really newborns and critical care. So clinical genomics, where you're actually diagnosing a patient. In the case of newborns, this is often the matters, a matter of minutes or hours can be significant in the outcome of a patient. We set a world record for clinical sequencing that I'll talk about on the next slide. So here, every minute matters. You don't want it to take 20 hours to sequence an individual. You want to be able to do that significantly faster. Similarly, in cancer, so when you're looking at the genomics in the context of cancer research, you're looking at the difference between a tumor sample and a normal sample. What's the difference in my DNA and my tumor versus the healthy tissue? And again, if in a clinical setting, minutes, hours, days, every bit of time helps in the outcome of patients. And sort of on the other scale, we have these large population studies. So there's many dozens of projects going on today across the world, funded by federal governments. In the US, we have All of Us program and the Million Veterans that look at these huge populations, up to 1 million people. Many are 100,000 or more. That just have a large amount of data that they need to process. And in these studies, it's not necessarily really important to be able to get a result in 10 minutes or 20 minutes, but you need to be able to do things much faster if you're going to do it 1 million times. If it takes a day, it's going to be months and years before you can analyze all that data. So speeding up for those large studies is very important too. And then finally, any research. So researchers want to get their findings published as quick as possible. So accelerating the computation there means publishing faster. It also means less time waiting for the computer to spin and give you a result. So more time actually doing research and less time sitting around drinking coffee and twiddling your thumbs while you wait for the analysis to complete. So I briefly mentioned this world record, and it's a great example of showing how the informatics or the computational part of the genomics workflow has become more of a bottleneck over time as sequencing has sped up. So you can see here the Guinness World Record that was set by Stanford University in collaboration with NVIDIA, Oxford Nanopore, and Google was at 7 hours and 18 minutes. And this is all the way from collecting the sample from the patient to actually delivering the diagnosis 7 hours and 18 minutes later, which broke the previous world record in half. So a really significant upgrade there. And you can see the wet lab portion at 4 hours, 48 minutes was essentially equal to the informatics or the computational portion at 4 hours and 46 minutes, meaning today that informatics portion is just as much of a bottleneck time-wise as the wet lab and the sequencing portion. So we need to accelerate that further to make sure that is not the case and we're getting results as quickly as possible. So I'm going to take a quick pause here, and you should see a poll question come up in the chat. The question is about what compute infrastructure you're using for your genomic analysis today, whether that's CPU or GPU based. And so please take a few seconds to answer that question, and then I'll move on to the next slide. Okay, so it looks like, I'm not sure if you can see the results, but about 69% said that they're using CPU-based infrastructure and about 34% are using GPU-based. So there must be some overlap there, but more on the CPU side, which is not surprising because there's lots of these open source and standard tools built on CPU infrastructure that have been in the industry for a long time. So just to talk about how we take that CPU-based tools and accelerate on the GPU, we take about 5% of the code, which can result in 95% of the compute time, and accelerate that and port it over to the GPU. So what a GPU is really good for is parallel processing, right? Doing thousands and thousands of operations at the same time, whereas a CPU is really good at serial, doing one after the other. But many tools and algorithms in genomics can be processed in parallel. So by porting some of that code over to the GPU, we can get the same results, but 50, 80, 100 times faster. And that's what we do across NVIDIA, whether that's genomics or an AI acceleration. That's our strategy to accelerate this code. And there's been a lot of momentum for using GPUs for genomics in just the past year. Some are highlighted here. Many cloud platforms, many genomics companies that are using Parabricks and GPUs to accelerate their workloads. You see the Guinness World Record there. In addition, long read sequencing, talking about just genomics momentum in general, was named the method of the year last year by Nature. This is a technology that's sort of the latest generation of sequencing that looks at longer reads or longer bits of your DNA than short read sequencing, and is led in the field by some partners of ours like PacBio and Oxford Nanopore, who have actually put GPUs into their sequencing instruments to accelerate the on-instrument analysis. So there's sort of two levels that we do this acceleration at, right? There's the hardware level and the software level. At the hardware level, we put our GPUs on board sequencers like PacBio and Oxford Nanopore to address the base calling, the generation of the ACTs and Gs of your genetic sequence. Oftentimes that's an AI-based algorithm that GPUs are well suited to accelerate. And then for the data center scale, when you have lots of data, and we're going to be talking about this, Bikash is going to go into some benchmarks, you need to be able to scale your secondary analysis workloads. So addressing volume with scalable solutions, whether that's in the data center or the cloud, and our DGX systems with the Pure FlashBlade is a great solution to help scale up there. Then finally, on top of that hardware, we have full stack solutions, which I'm about to go into, that software that is built to run on the GPU and accelerate your traditional genomics tools 50 to 80x faster. All right, I know we probably have a mixed audience here, so I'm not going to go too deep into what the computational genomics workflow is, but gonna run through it quickly to give some context to what's happening here. So we break down the workflow into three basic steps. There's the primary, secondary, and tertiary analysis. In the primary analysis, this is typically done on the actual sequencing instrument. The first step is DNA base calling. So that's when you have this electrical signal or visual signal that is converted into those ACTs and Gs that make up our genome. Typically, today, a lot of sequencers use AI-based algorithms to make this process faster and more accurate. So they use GPUs to do that inferencing with tools like TensorRT. Once you've done the base calling, there's some error correction and polishing steps just to improve the accuracy of that base calling that also can run on GPUs. And then finally, we have these reads that the sequencer outputs, which I mentioned before, long reads and short reads. There's different technologies there. Essentially, when you sequence a sample, so if you were to sequence someone's DNA, you're not able to do it all the way from the beginning to the end. It's 3 billion base pairs long. What the sequencer does is essentially reads them in chopped up sections. So for short read, that could be 100 or 200 base pairs long, 100 ACTs and Gs. Or long read can be thousands or hundreds of thousands, but still nowhere close yet to 3 billion. So what we need to do is take these short fragments of DNA of the ATCs and Gs and assemble them together or align them together into the entire genome. So it's basically fitting puzzle pieces together, and with only 4 different letters, you can imagine that is a computational task that is not too easy. So we've accelerated that process on GPU with Parabricks, as well as the next step, which is variant calling. So this is really where we get into the interesting part of the genomics analysis, where we're looking at the differences between an individual's genome and the standard or reference genome to figure out if they're predisposed to have any disease or make a diagnosis. Or again, in the case of cancer, you're looking to see, is there a variation or a variant that's in their tumor DNA that's not in their normal DNA? And that step is variant calling, also accelerated on GPU with Parabricks. And then finally is the interpretation or modeling, where you're actually looking at those variants saying, oh, I have an A where this other person has a T, or the standards to have a T. That means X, Y, or Z. So here you're pulling information from different databases to do that interpretation and make a diagnosis and recommendation at the end of the workflow. That was my whirlwind tour of what happens across the computational genomics workflow. And I'm going to go into a little bit more detail on Parabricks specifically. All right, so Parabricks is accelerated secondary analysis on GPU. And there's sort of 4 focus areas that I'm going to highlight here. The first is key applications. So if you are a bioinformatician or familiar with these tools, you'll see at the top here the tools that are in Parabricks. These are common industry standard, gold standard tools. So, BWA MEM, deep variant haplotype caller are used by thousands and thousands of people across the world. But traditionally, those tools run on CPU and are very slow. So what we do is we accelerate them on GPU while providing equivalent results. So you get the same results, but accelerated 50 to 80 times faster. And with that acceleration, not only are you getting results faster, oftentimes you see significant cost savings, because even though a GPU on a one-to-one basis is more expensive than a CPU typically, it's not 80 times more expensive. So on a per sample basis, you can see upwards of 50% cost savings by the efficiency of the acceleration of the GPU. Third feature here is flexible workflows. So this is fairly new to Parabricks, where we now support WDL and Nextflow, which are common workflow languages used in genomics and bioinformatics, make it much easier to customize your own workflow and scale it out across different infrastructure. So, you don't have to go end to end with Parabricks. We have many customers that choose certain tools within it and might have their own proprietary or preferred tools for variant calling. These workflows make you combine Parabricks tools with anything else that you'd like, and specify the infrastructure and make it easy to scale. And then finally, accuracy of paramount importance. Doesn't really matter how fast you get results if it's not accurate, right? So we always aim to meet or exceed the accuracy of the tools that we provide. Great example of that is Deep Variant, which is actually an AI-based variant caller that uses convolutional neural networks to actually look at the pileup images of the reads to detect if a variant is true or not. And this has been shown to be more accurate, this AI approach, than traditional variant caller tools. In terms of the acceleration we see with Parabricks, here are some of the more commonly used individual tools within Parabricks. You can see the CPU runtimes highlighted in gray. So, 4, 9, 16, 5, 31 hours, significant amount of time. And this is for a single sample, 30x whole human genome. Versus the green times highlight the GPU performance. And this is all run on a DGX A100 system. You can see we go from 4 hours to about 11 minutes on the alignment step with BWA MEM, 31 hours to 45 minutes with MUTEC 2, which is a somatic variant caller. So really X order speedups, again, that 30 to 80 times faster, depending on the tool. And then Vikash will show some overall performance numbers that we achieved with Pure for entire pipelines later. So again, not just higher speed, but that higher speed also typically results in lower cost. So we actually have a collaboration with the Broad Institute, who, if you're familiar, are the ones that actually develop and publish GATK, which is the gold standard genomic analysis toolkit used by the industry, but typically runs on CPU. And we have the accelerated version of that on GPU. So we worked with them to verify that our workflows produce equivalent results to their CPU native tools. And they also did an analysis on the runtime and the cost. So they went from 24 hours on their CPU tools to under 2 hours on the GPUs. They were using some lower powered GPUs. And then on the cost, they went from $5 to $2 per sample. Again, this was on a 30x whole human genome. So that's more than 50% cost savings on a per sample basis. Really adds up, especially in those 500,000 sample type projects. One quick example of a customer using Parabricks on the DGX A100 is the National Biobank of Thailand. So this was actually used for one of those population projects, the Thailand Genome Project, where they were sequencing over 50,000 individuals. By using Parabricks on the DGX A100, they achieved 30x faster analysis versus CPU and a 93% overall reduction in their data processing time per individual. And basically, it sped up their analysis overall by 4 months, which is more than just a few minutes or hours. How we make Parabricks available today, there's sort of two different ways that you can consume Parabricks. And this is new as of late last year. There is a DIY version or do-it-yourself, where if you just want to take the tools, build something yourself, use it as it is existing, it is completely free and open. The containers are publicly available on NGC. NGC is NVIDIA's container repository, so they're available as Docker containers. All the tools and workflows are available that way. And we have a community forum where you can go to ask questions or get advice and get support that way. If you're a commercial organization and doing this in production and at scale, you might want to have the guarantee of enterprise support. So for that, we offer a support subscription called NVIDIA AI Enterprise that covers both Parabricks and lots of other software tools from NVIDIA too. So it's a great value and provides benefits like long-term support and updated security reviews and notifications. And I will share a link to where you can find the Parabricks container if you're interested in trying it out in the chat later. All right, so that's sort of Parabricks as it is right now. Looking a little bit to the future, we have a new release coming out in later this year, about a month and a half from now, which is going to be Parabricks 4.1. So 3 things to highlight and get excited about for 4.1. The first is further speedups. So I mentioned you could do a whole human genome in as little as 21 minutes in version 4.0. And 4.1, our engineers have made that even faster, currently getting results as fast as 16.5 minutes. So significant improvement in speed there. And that's just on the same GPUs, right? It's not upgrading the hardware, it's just switching to the newer version. We have new hardware coming too, like the H100, which is the latest high-end GPU from NVIDIA that we'll see even better numbers on in the near future. And then second is we're excited to have long read support for the first time, an end-to-end workflow for long read for PacBIOS specifically. Minimap 2 accelerated version is coming, which is a different aligner used for long read workflows, as well as an updated version of Deep Variant. We'll have Deep Variant 1.5 in Parabricks 4.1. And then finally, this one's actually available now, prior to the 4.1 release, is a retraining framework for Deep Variant. So I talked a little bit about how Deep Variant is an AI-based variant caller. What that means is it's a model that you can train. And it typically was very difficult to retrain and adapt that model to different data sets. You basically had to work with the Google team to do that. But now we've created this framework that makes it really easy to retrain and fine-tune on your specific data. So the data generated by each genomics lab is slightly different. You might use slightly different kits. You have a different environment, different methods, and that can affect the accuracy of a tool for a specific lab. So by being able to retrain and fine tune that on your lab's data, you can significantly improve the accuracy of the deep variant model for you. And we've worked with numerous customers like Regeneron who have done this already and seen significant improvement in accuracy for their whole exome model. As well as a lot of the upcoming and emerging sequencing technologies who are looking for a custom deep variant model that works best with their sequencing data. All right, as I start to transition over to Bikash, who's going to talk about the combination of the GPUs and the DGX system with the Pure FlashBlade, it's really important to talk about how we can bring this to scale, right? So a lot of the numbers I shared were using local storage, but once you're doing more than a couple genomes, or you're doing hundreds or thousands, you really need to be able to scale that up and have a different storage solution than local. So Bikash is going to go over this architecture that we've created together, and we have an asset that we'll share too with Pure, combining the power of the DGX and FlashBlade. That's a great solution, not just for genomics, but lots of applications in AI and HPC. So as I do hand it over to Bikash, who's going to talk about this solution for solving the tremendous amount of data that's being created. I've covered the computational platform with the accelerated genomics on GPUs that's scalable. He's going to talk about how we need the I/O to keep up with that GPU processing and how we can solve for that, as well as the ability to store thousands of samples. And typically we're storing samples in multiple file formats too. You might store the FASTQs or the BAMs, which are the aligned reads, or the VCF, which is the file once you've called all the variants, or a combination of all three in different places. So we need one solution to work with all of that. Awesome. So as I hand it over, there will be another poll question appearing in the chat. And this question is about where you are running your secondary analysis today, whether that is on-premise in a compute cluster you have, or in the public cloud, or on a hybrid cloud. So I'll give you a few seconds to answer that, and then Bikash will go right into it.
All right, thank you, Jason. And thank you to everyone who answered the second poll question here. Looking at the results, it looks like 50%, I would say, are still on premise, and there is an overlapping between a public and hybrid cloud, where I guess you are operating both in on-premise and also in the cloud. That's something really nice to learn about. The amount of sampling, the processing that you're doing is extending to cloud from your on-premise setup today. All right, so we heard a lot about data, Chad, the growth of data in the genome samples, and it's been exponential. A few other data points I'd like to reiterate that Jason mentioned during his presentation was about the flexibility, the workload types, and the accuracy. Those are the three main areas which I think is very, very important when you're actually processing a lot of these samples. Now, when you look into the data and the growth of the data, that is absolutely chaotic. That means data has gravity. When you're doing it in a local storage, when you're having a small number of samples, just like what you heard in the previous part of the presentation, this all looks great, but things start to change when you start to have a high magnitude of samples that needs to be processed. And that is where it is being extremely challenging, not only effective I/O that goes back and forth from the computational platform to the backend storage. And there are a lot of different storages available, but specifically what Pure Storage does, it is capable of actually scaling not only the capacity that is needed for any number of samples that you would like to store, but it actually provides a standard data platform for your entire pipeline. And the reason why I say that is you would normally notice that you start off from a primary analysis. Obviously, the focus of this presentation will be on the secondary analysis, but when you go through the primary analysis, you still have a different kind of an I/O pattern. And that I/O pattern is very different from the secondary analysis. Now, when you have separate kind of storages or in isolation or in silos, it becomes a lot of challenging thing when you're moving data across, because I remember when I was moving my FASTQ files from a primary analysis to start with into secondary analysis, that took me a lot of time. It was almost like a couple of hours or less than 2 hours to literally move those files over to my secondary analysis before I can kick off my secondary analysis. So that is a lot of time that you spend when you're actually moving data around. Why do you do that? It's not needed when you have a standard platform, because Pure Storage has the ability to actually do this processing as a standard data platform for any kind of an IO pattern or access pattern that is needed for the different phases of this pipeline. So it is scalable, and obviously I will touch upon the data services in a moment here, what Pure Storage can offer. So this is exactly what I was talking about. Is a simple, scalable, high performant, and it has got various different data services. I'll be touching upon that. And you don't have to own the storage if you really don't want to have that. It is completely an OpEx model that we can offer. All you care is your data. So you don't really have to own the storage. All you need to access your data. That's exactly what we can offer. And we can actually have so many different kind of workloads that can run, just not in genomics, but there are so many other use cases and other workloads you can actually be running, because in today's world, there's so much amount of integration that is happening. I'm not trying to say that we are completely 100% a Swiss knife army, so completely a Swiss knife. But at the same time, we have that ability to handle a lot of these what you call file-based unstructured data that you normally find in today's modern data setup. Whereas we do have other offerings which can actually handle a lot more structured data sets, but specifically speaking in the genomic context, you see a lot of these unstructured data, and that is exactly where Pure Storage can come in with that platform, which we call as a FlashBlade. We'll learn more about it as we move forward. So we talk about Pure Storage. Who are we? And this is a company we've been started, and we've been growing at a 26% year over year. And the biggest thing which I would like to draw your attention is we are loved by our customers. We have got 81.4 NPS, it's the highest in the industry. That's the key thing, because yeah, we all do businesses, but the customer rating that we get is outstanding. So where we are in the industry, we are definitely in the leader quadrant, and we are leading along with in this space from a file perspective, because that is where this entire solution is being based on. So the entire application that you run in with the Parabricks and the compute platform on the DGX A100, it is using a file access to the backend storage, and that is where we see that we are a leader in there. And we also have this journey when we started off, because you do see there's a lot of other storage vendors over the years, but the place where we started around 2009, and we moved on so far with so many different product offerings, but we will be focusing primarily with the FlashBlade, which I was mentioning. It is a file and object offering, and we've got so many other data services that can actually be benefited to the entire genomics sequence processing. The reason why I say that is if you just store your data, which you can absolutely do that in your local storage with the number of samples you really like to process. But over time, when you're actually having multiple samples and the number of samples kind of grows, and you started to do a lot of genome sequencing for your next generation sequence process, what happens is you tend to generate a lot of files, and you need to protect those files. You need to manage those files. You need to also get the performance numbers. Like for example, you ran a process on a particular sample, and for some reasons, you need to rerun it for an error that has occurred. So how fast can you revert back to a clean set of data that you started off without any results or any kind of an vertical data set which doesn't have those errors that you had, and then you can retest it again. So those kind of services at a data layer is very compelling, because that actually enables the end user to move forward with this processing a lot more faster. And this one, I would like to talk about the area that Jason was pointing out earlier in the presentation, that this is where we actually are focusing in this this offering, and we are using FlashBlade, and this is our entire portfolio that we're having. And if you look into this, you'll see that this is an entire a converged infrastructure, which is out of the box. You can get it up and running, and you can run your Parabricks or any other AI or HPC workloads on it. So when we look into the FlashBlade a little more deeper, as I was mentioning, this is mostly a file and object offering because for genomics specifically, we are still sitting on a file access at this time. But in the future, if you do have any applications that is related to your genomics pipeline or any other HPC workloads, you can still communicate or set it up or on objects too if there is an application that supports object in the backend. But let's focus on the file services alone, which is NFS based. And then you have got the snapshots, the replications, like you have got sites that you need to collaborate, or you want to have a DR site where you would like to save your files for a long-term retention. Then security of your data, that is absolutely important because you got to have not only the data security at rest, but what happens when you're hit with a ransomware and you really want to protect your data at the time. And then at the same time, we also have the ability to move to cloud. And that's the reason when I saw that answers to the poll question, the second poll question, I was really amazed at the amount of hybrid cloud and public cloud setups that normally you are using it in your existing infrastructure. So we have that flexibility to move data to cloud, and that's a huge enabler for even for what do you call businesses who are running on a hybrid cloud environment. And just to touch upon a little bit on the array part that we talked about, this is again a brand new platform. We had an array offering, but with the new platform that Pure Storage launched last year, that is FlashBlade S, we have revalidated that again. And this is the genomic solution is actually based on the newer platform that Pure Storage launched. That's called FlashBlade S. And it's got a lot of these functionalities, the ease of management, the efficiency, the scale, the agile AI platform, and obviously because NVIDIA and Pure Storage has been industry leaders, as I showed you earlier in the previous slide, and that it alone coming together is a huge advantage because we stand behind this, not only the product but the solution offering that we are making today with Parabricks and FlashBlade. Now let's look into the actual validation that has gone into this particular solution here. So if you look into the entire workflow of a genome sequence process, you start off with the primary analysis, go through the secondary, and then you can move on to your tertiary. And what I was trying to say in the beginning is there is data everywhere. And the kind of data that has been generated, the access pattern is very different from a primary analysis to a secondary analysis. Now, you may have started off with a CPU-based infrastructure with data being completely localized on your local servers. But what happens is not only the pipeline is going to slow down over a period of time, but at the same time also have the ability not to collaborate or move on from a first phase to the second phase to the third phase, or even there is a way of collaborating different samples at the same time, it becomes a huge challenge because I was mentioning, as you start to explode with data, managing the data is extremely challenging at some point of time. So we keep an eye on all of these different phases that can actually land in this on a FlashBlade, which is going to be a standard data platform, and you can actually grow and scale your data as needed. And there are so many different data services that we have today, which can directly help the end users, not only the admins, but the end users to rerun the test, reanalyze the test on demand. It's nothing that you have to wait for anything. It's done on demand, and it's very quick and instantaneous in some instances where you can literally get this thing rerun again when you are going through this entire process. So the test environment. We did run it with CPU based, which is using a GATK, and we ran it on the same platform. And then we also ran it on an array, which is you see on the right hand side, which is obviously Parabricks is completely GPU based. We ran the germline pipeline for this test. And if you remember in one of the slides, Jason was pointing out of how Parabricks versus any other CPU based has got a huge difference in the time it takes to reduce the entire, the analysis portion of it. So I'm going to connect those dots as to what happens when you put that on a FlashBlade. As I was mentioning earlier, it's not just the data, the volume of data that has been stored, but it's also the I/O, how fast we can respond to some of the various different parts of this process, right? When you pick up your input files as a fast queue, all the way you can get your variant calling files. Now, that entire duration is how fast you can run it. And obviously we saw some numbers that Jason provided just alone on Parabricks. And then what happens when you drop that into a FlashBlade, right? So these were the different samples we picked up for this particular test, and there are 5 of them. And they have got different capacities as well as different coverages. So every sample is going to be different. We just can't put a finger on one sample and say I got this much amount of speed on a particular sample. That doesn't mean we'll be getting the same speed on a different sample. So every sample is different. So these are the numbers. Again, these are numbers which are compared against a CPU platform. And these are running on Parabricks, which has got, you see those 2 GPU, 4 GPU, and 8 GPU. This is where we try to see if we were start with 2 GPU, what the numbers look like. Obviously, the best numbers we got out of 8 GPU when we're running that on the DGX A100. But the thing is that you see the faster the time, the speed up time you see on each of these samples, they are different. And if I were to just go and pick one of these samples, which say the NA24385, which is the second one in this entire list, you'll see 33x faster. But what is it actually transpired? So this is where I would like to highlight the data point here, 2 points here. First of all, you saw in the previous slide that went down from 33 hours to 45 minutes in that slide, which you're using local storage. This one went from 45 minutes further down to 27 minutes when it is running on a FlashBlade. So that additional time that you get. Now, if you look into the overall big picture with Parabricks running on FlashBlade, so which took about around 880 minutes, went down to 27 minutes. That means with 880 minutes, which was taking that on the CPU, you're going to do the math to calculate how many number of samples, of similar size samples you can do in a year, versus when you go down to 27 minutes and how many number of samples you can actually accelerate on this entire platform in a year. So that math alone can give you an indicator that we are about 33x faster. When I say faster, means number of samples that you can actually process in a year when you compare that with the CPU-based platform versus a GPU-based with the FlashBlade as a storage layer. So that is the difference when you see how the storage can complement the already fast Parabricks pipelines that we see on running on GPU. But the storage itself alone can actually complement a lot of things. There are a lot more technical stuff that we have done, and has been captured in our white paper, which I'll be showing you later in this presentation. But if you're really interested to understand more what exactly has happened in this testing, please reach out to us, and we'll definitely can work with you to give you the details that has gone behind the scenes. Now, on the storage side, when we were running this from a 2 to 4 to 8 GPU, you see the I/O side, the linearity, the scale that you normally see, because if you remember, it is just not the performance of the storage capacity that we're providing, it's how does the performance scale? Like, for example, if you start up, because everything has got a cost to it, and keep in mind, right from the beginning, we're trying to say we are going to reduce our cost for this entire genome sequence. So if you're going with the 2 GPU, yes, you do have a very good I/O going back and forth from the compute layer to the storage layer. But as you start to add more number of GPUs, you run faster. And that's where I was pointing out in the previous slide, with GPUs, with 8 GPUs, you're obviously finishing it a lot more faster. But you run that, we were running all the 5 samples at the same time. It is not like it was running one at a time. It was running all the 5 samples at the same time. So it took different time for each of these samples to finish. But at the end of the day, when you look at the storage perspective, there is a complete linearity in the way you actually try to scale 2 or 4 or 8 GPU. Now, from an accuracy perspective, as I was mentioning, and Jason was pointing out earlier, that we've had to look into the accuracy part. And we are about a 96+% accurate, which is allowed under the GATK accuracy levels, and in some of them, and most of them we are 100%. So what that means is, if there is any inaccuracies or there are errors that you'd like to rerun this, the data services that we are providing on the FlashBlade will really give us that ability to go back and rerun your test if there is any chance that you'd like to see better results on it. Now, to summarize what we found out is, or I like to at least infer from the testing we've done, is it's all about the standard data platform I was mentioning. There is a huge growth in data, and the access criteria for the data is different. The signature is different as you move from a entire pipeline from left to right, that is primary to secondary to tertiary. And so it is all about giving them the best cost efficiency in ROI, because as you start to grow your number of samples, you need capacity, you need better IO, and every phases have got different signatures. And the other one is the speed. The number of genomes, what exactly doesn't matter if I get a infrastructure that is really good enough or fast enough for me. What that translates is you can actually go up to a high number of genome samples that you can process in a year. And that gives you an ability to actually even reanalyze when you're having errors, and running your clinical test a lot more faster. And the third thing is about scale, speed, and simplicity. Yes, you can actually get high number of samples now processed, but again, the infrastructure also has to support that. And that is the reason where Parabricks with GPU and a FlashBlade, which is the ARE model that we were talking about, kind of complements the entire process when you're sequencing so many number of samples at scale. So this is a QR over there. If you would like to scan that and check that paper out, it's got a lot of good information. We're willing to collaborate on understanding, help you explain if you have any questions on that. At this time, I would like to have the third poll question, which would include as to how many genome samples are sequenced in parallel today in your organization. Great. I think there's also great. So we got a sweet spot of 20 to 30 samples in parallel, but there are also people who are running more than 100. That's 50 to 100 and 100 greater than 100. So that's a good number too. So thank you very much for your answers to the third poll questions.
Yeah, a good variety there. I think we have a few minutes to answer some questions from the Q&A too. So if you do have a queue, you can put it in there while we answer some of the ones we already got. One that was interesting that I saw was about ChatGPT and data challenges there. So maybe ChatGPT itself isn't super relevant to genomics research today, but it's actually an interesting topic because ChatGPT uses large language models, right, to understand human language and provide insights to prompts. There's actually similar work being done and has been done to apply large language models to the not human language, but language of biology, right? DNA or protein sequences. So that is a really large area of research and an application of AI and deep learning that we're seeing in this space. One example that was actually won the Gordon Bell Award at supercomputing last year was this model called Gen SLM, which takes the ATCs and Gs, the DNA language of a COVID virus, of a variant of the virus, and then can predict whether that is a variant of concern that researchers and the government should look at, just based on running that sequence through a large language model. So that certainly will increase the amount of data and AI used in genomics in the future, those biological large language models, sort of similar to ChatGPT. So it would be cool if you could just one day, prompt these biological language models to ask, oh, what does this sequence mean? Like what, and it'll output, what disease you might be predisposed to, but we're not quite there yet. Another good question I saw was about using Parabricks with consumer grade GPUs. So we consumer grade, if you're not familiar with NVIDIA, we sort of have two lines of GPUs. We have what we call our GeForce cards, which are traditionally used by gamers or in consumer workstations or PCs. Then we have our enterprise grade GPUs like the DGX A100, T4s, V100s. There's lots of those. So we test on the enterprise grade GPUs. Those are the GPUs that we've designed and engineered to run 24/7 in a data center environment that are well suited to genomics analysis workloads. So that's what we've tested it on. If you have a consumer GPU that meets the minimum requirements, it could work with Parabricks. We just haven't tested them. And we won't provide support on those GPUs, but you're welcome to pull the container and try. And I will also make sure to send those requirements via the chat. We have some documentation. And then the last question that I also see is about Parabricks and DGX comparing to Illumina Dragon. So Parabricks runs on GPUs, right? Which is a much more general purpose platform. So you can use that same DGX for running Parabricks or for doing base calling for Oxford Nanopore data or for protein folding or for training your own AI model. So it's a much more generalized piece of hardware that can be used for multiple purposes and give you a lot more value that way. Specifically comparing the two, Parabricks, I think especially with this 4.1 is as fast or faster. And has equivalent results to those open source community tools and doesn't require a license. So those would be some major differences I would list.
Okay, so how do you deal with it in the case it crashes? I don't know if the video say when it crashes, it means crashing the pipeline alone or the infrastructure crashes. So I'll try to answer the question about the crashes and the infrastructure, the storage part of it. So on this, if it crashes, I don't think we have got high resiliency, by the way, high availability. So the failure rate is very, very minimal in our case. And I would say that because we have got a protection layer of data in the way we are writing the data, the backend storage, not to go into the details of that, but we are well protected from your data perspective. So if there is any connection that is missing, you lose your connection between your computational layer to the storage layer, you restart whichever the process of that is going on in the computational layer, you can connect to the data right away. Because it is NFS, you can always connect to that right away. It is highly resilient, and you can still continue to access your data. So from a data failure perspective, is almost none on the storage, and that is the biggest part also that we are offering of the high high availability that we have, and with no data loss at the time. So you can obviously access your data as soon as you can get online if you are losing your network connectivity to the storage.
All right. Thank you so much to Bikash and Jason. Really excellent presentation. A mind-blowing topic for a Friday webinar. I learned a lot. I'm sure everyone out there in the audience did as well. Thank you to everyone for the excellent questions. We are routing these over to the Pure Storage and NVIDIA team. And with that, it is now time to announce the winner of our Amazon $250 gift card prize. This is going out to Alex Solodukin from Virginia. Congratulations. Alex Solodukin from Virginia. We'll reach out to you, and I hope that everyone has a great weekend. Visit purestorage.com and nvidia.com for more information. Take care and have a great day. Bye-bye.